So we're going to go through some different cases of how we can find exponential functions. So these cases I separated based on what information they give you, and then we'll talk about the steps to finding the exponential function given that information. Alright, so our first one here. So when I'm talking about these letters in the context of that our exponential function is a times b to the x, where b is made up of 1 plus r, where r is typically a percentage growth or decay. So when it says given a and b, the idea is that they're just giving us the initial value and the growth rate. So write an exponential function with an initial value of 12, so that's giving us a, and b value of 0.98. So this is the most direct case where we just have to write those numbers in. So initial value of 12 times 0.98, and then we just need our variable in the exponent, and that's that one. Alright, case 2. Given the value of a and r, so the initial value, another way it can be given is in function form. So this is where x is 0 and 35, so it's like the coordinate 0, 35. But what all of that tells us is our function starting at 35, and that's our value for a. So we're getting a is 35, and then we're getting that our function is growing at a fixed rate of 0.53. So to calculate b, what we're going to take is 1, since it's exponential growth, we'll be adding, and then 5.3% is the same as 0.053. So remember to be careful moving that decimal around. So it's moving the decimal to the left 2 spots, so that's where we get the 0.053. Now, don't round here. In fact, that's something I'm going to emphasize a lot here, is that don't round until the very end, especially with exponential functions. If we round too early, it'll completely throw off the equation and we'll have a lot of error occurring. So I'm going to keep that as 0.053, and adding those together will be a 1.053. Alright, so with that, I have my value for b now, I have my value for a, so I have my function f of x is equal to initial value of 35 times base of 1.053 with our variable in the exponent. Alright, so that's case 2. The main difference being that they give us r instead of b, so we just have this extra step of calculating b. Our next step here is they give us our value for a and a coordinate. So suppose the price is growing exponentially. Initially, the price was $28, so that's our value for a. And then 10 years later, the price is 50. So what we could do is just make time that t starts at 0, and then we have this point that 10 years later, so t is 10, and the price is 50. So something I'm going to make a mental note of here after reading this sentence is that the price grew when it changed. So with that, I should be getting a function that represents exponential growth because the price is getting larger with the passage of time. So I'm just going to kind of store that in the back of my mind while I solve through this. So what I'm going to do is start the structure of my exponential function. So with that, I have p of t equals my initial value of 28. I don't know what the growth rate is, so I'm just going to put b there and then our variable of t. Now what I'm going to do is plug in the point that we have. We know that if t is 10, then p is 50. So I'm going to plug that in of 50 equals 28 times b to the 10th power. And now what I'm going to do is solve for b. So I would divide by 28 first. Now this is a spot where I'm not going to round. So I'm just going to keep that as 50 over 28 to keep accuracy. You don't even need to reduce it down because eventually it will go into a calculator. So you don't need to worry about simplifying so much. We can make it kind of messy, but exact is our key idea behind this. So then we're going to have b to the 10th. Now, the rule we're going to use here is a way of canceling out exponents, because basically I have the variable I want to solve for is trapped underneath an exponent. So what I need to do is create an exponent of 1 here. And how I can do that is I can raise this side to an exponent of the reciprocal of the exponent. In short terms, we're just making a fraction with that exponent in the denominator. So what that would look like is 1/10. Why we're doing this is because power to a power rule has us multiply those, and 10 times 1/10 will give us 1, which is exactly what we want. So what we're doing is we're choosing an exponent such that they'll basically cancel out with each other and we'll just be left with 1. Now whatever we do to one side of the equation, we have to do to the other. So what we're going to have from this is, on the right hand side, that 10 and 1/10 will just cancel out, so we'll have just b. And then on the left hand side, I need to plug that into a calculator, and then we can round it to a decimal. So I'm going to go to a calculator, and we'll have in parentheses 50 divided by 28. And then in the exponent, we'll have a 1/10. Sorry, I just want to see if I need those parentheses there. No, okay, you don't need to use parentheses for the fraction exponents. Just when you start adding and subtracting things in the exponent, you'll need parentheses to group them. So we have this number here, and what we want to do for accuracy is keep it to at least 4 decimal places. I'm going to go to 4 decimal places. The more you include, the better. That'll make the function more accurate. So I'm going to go 1, 2, 3, 4. And that 9 is going to have me round up. So I'm going to use a 1.0597. All right. So we have our value for b. We have our value for a. So now I have my function p of t equals 28 times 1.0597 to t. Okay, so if you're given a and a coordinate, then you'll plug in your value for a, then plug in the coordinate, and you'll be able to solve for b using those pieces. All right. Given a graph, so with it, or it's not even just given a graph, we're given the value for b and we're given a coordinate. So we have our coordinate coming through right here with this 847.025. We could use that as a comma, or it looks more like a decimal to me. Let's say it's a decimal and go with that. So our value for b, and actually they gave us r, but that's the same thing as giving us b. So b, it's decaying, so we have 1 minus, and at a rate of 9%, so 0.09, which is a 0.91. So I'm going to start the structure of my function. So this is our function f of x equals, and we don't know a, times 0.91 with a variable or exponent of x. All right, so now what we're going to do is plug in the coordinate and solve for a. So I'm going to go 47.025 equals a times 0.91 to the power of 8. Again, where we could simplify 0.91 to the 8th power, I'm going to leave it just like that because I don't want to round anything yet. The idea is whatever number would come out here, I want to divide both sides by that number. So I'm going to divide both sides by 0.91 to the 8th power, 0.91 to the 8th power, and that's going to give us our value for a. So I'm going to go ahead and type that into a calculator. So 47.025 divided by 0.91 to the 8th power. And we're getting 99.9995. 99.9995, which might just be 100 if this wasn't rounded. Let's keep it exact, but I could hear the argument that that's probably 100 because these starting values, these initial values are usually whole numbers. But we don't want to assume too much, so let's keep it accurate. Stick with these rounding rules. 5 times 0.91 with an exponent of x. Something I want to note about graphs, when they give you information, even if it was labeled in fact, I'm glad I left it at 99.995, because if they'd done this, with a graph that's kind of not abstract, but it isn't really clearly defined as other graphs, without that actual coordinate defined, I wouldn't want to assume I'm actually crossing through 100 there. I want to be careful of, like I said, assuming too much, because when we get into the calculation of it, maybe it's just ever so slightly smaller than it. So typically it is going through a whole number. We want to be careful in that I know I have this value for b, I know I have this coordinate, so even if I saw that 100 right there, I would maybe want to ignore it because it didn't clearly define the coordinate 0, 100. It's just giving me a scale for the number line. So just want to be careful there. Okay, our last point here is given two coordinates. So we have this coordinate 545.3, and what we're told is that doubles in 7 years. So 7 years have passed, but we were already at year 5. So what I'm going to do is 5 plus 7. So really we're in year 12. So it doubles in 7 years. Just be careful of the wording there. And that means the output doubled. So 45.3 times 2 of 90.6. So we have these 2 points. Now, this is a scenario where there are lots of different ways to do this. And there's long routes. And what I'm going to show you is just the short route. But there are other ways to do this. So if you find a video with a method that you like, absolutely go for it. The long methods of this take a long time. But if you want to see it, message me. I'll make you a video for it, but typically my students like this short method, just because it is so quick compared to the others, but there are other ways of doing this. So what I'm going to do is, if I think of my function setup, so I'm just going to use f of x equals a times b to the x. What I'm going to do is plug in both of these points. So what that would look like is 45.3 equals a times b to the 5th power, and we have 90.6 equals a times b to the 12th power. What I'm going to do is take these functions and stack them on top of each other. So one's going to go on top and one's going to go below. A little trick is the one that goes on top, things become a lot easier if you put the higher exponent for b on top. What I mean by that is, in this case, comparing the 5 and the 12, because that 12 is larger, I'm going to have that be the top function. So I'm going to go 90.6 equals a times b to the 12th power, and it's because, I'll make a note of this, because it's the larger exponent, put function on top, or equation rather. And then the other function will go below. equals a times b to the 5th. Okay, so the trick with this is now that I've stacked them, what I'm going to do, and this is where, like, it's hard to explain, or it just takes a while to explain why it works, but if you're good with just going ahead with it, awesome. If it's uncomfortable, then you might want the longer route, because the longer route does make more sense. But what we're going to do is divide. We're going to do this division between the two functions. Now, the equal sign just carries down, so make sure equals carries down. On one side, we'll have this 90.6 divided by 45.3. A divided by A, those will just cancel out with each other, which is awesome because then we only have one variable left. And then for B, our exponent rule says take 12 minus 5, which is 7. So we can essentially do this because all of our work comes down to multiplication and division. So it's not too awful to divide things. If we had addition and subtraction anywhere in here, it would make a mess of it. But because it's all multiplication, this works really nicely. Now, this is the reason why I wanted to have the larger exponent on top, because if you can imagine we switched it, you'd end up with a negative exponent, which isn't the end of the world, but you'd have some extra steps there. So with that, I just like to set it up so that it's all positive. So having the larger exponent on top helps with that. All right, so our next step is I want to get rid of that exponent of 7. So I'm going to use that trick of raising to an exponent that's the reciprocal. So I'm going to do a 1 divided by 7, so that when I multiply those, it's just 1. And whatever I do to one side of the equation, I have to do to the other. So B equals, and then I'm going to go to a calculator. So in parentheses, we will have 90.6 divided by 45.3. And as an exponent, 1 divided by 7. So we're getting a 1.104. And I'm going to cut that off at the 4th decimal place. So a 1.1041. Okay, then with that, we found B. So now what I need to do is find A. So we could start the structure of our function. We'd say f of x equals A times 1.1041 with an exponent. And then just plug in one of the coordinates. It doesn't matter which one. Let's say we do the 45.3 equals A times 1.1041 to the 5th power. And I would divide both sides by that 1.1041 to the 5th power. 41 to the 5th power, and just plug that into the calculator. So 45.3 divided by 1.1041 raised to the 5th power, 27.6093. So our function is, yeah, let's keep it to 4 decimal places. With my open math, just follow, they state any rounding rules. If you can keep it to 4 decimal places, that should keep a good amount of accuracy. I know it looks kind of messy, but being accurate is good. We can check our solutions too, see if we plug in 5, if we plug in 12, how well it works. Now when we do that, these numbers are rounded, so we do want to keep in mind we might be a little bit off. But let's say we take that 27.6093 times 1.041 and raise that to the 5th power. And you can see it's off, and it's because I didn't type in the 1 right there. Alright, 45.3. Again, a little bit of error there, and that's just because we have these rounded numbers being plugged in. If we plug in 12, there's our 90.6. A little extra, but that's completely fine. It's close enough. So, with this case given 2 points, the steps go plug in both of the points, stack the two equations, and everything should be lined up. So you have your number on one side, a times b with your exponent on the other. It helps to stack it such that the larger exponent on b is on top. And then we're going to divide. So you'll divide the constants that are on one side of the equation, divide the other, which will cause the a's to cancel out. And then with b, you'll use the exponent rule with subtraction. Then you'll use that rule of raising both sides to the reciprocal of the exponent on b, so that turns into 1, and then you just plug into the calculator to get b. Once you have b, you can solve for a by just plugging in a point and solving. And just remember, use your calculator, try to keep it as accurate as possible all through your work. If it rounds, especially with exponent properties, it's just, if that number is too rounded, then you're exponentially growing that error that's on that number. So you just want to be careful.